And the peak here is I naught, V naught. Okay, the plot looks something like this. And you might want to see this plot from another viewpoint. Okay, if you remember your trigonometric identity, how can you replace cosine square omega t with? Does anybody remember the trigonometric identity for cosine of square of theta? One plus?
Cosine omega theta over 2 is equal to 2.
1 plus?
Cosine theta over 2.
The frequency increases. Before we square it, the frequency was like that. Right? And then we square it, it flips it around, and make the frequency go twice as long. So this must be something like this, right? And this follows from the identity that cosine of 2
I think
theta,
it's 1 minus cos 2 theta by 2.
cos squared theta minus sine squared theta. So if you replace it with 1 minus sine squared, it's 2 cosine squared theta minus 1. So the identity should be that cosine square of theta should be half cos of 2 theta plus 1. Okay, so this should be half. Did I derive it right? Okay, this follows from cos A plus B is cos A cos B minus sine A sine B, and then use that formula, you get this formula that cosine of 2 theta equals that, and then you use the fact that sine squared theta is 1 minus cosine squared theta, you get this, and then. So if you can't see this plot visually, then you can see this plot from another viewpoint. Okay, that there is a sign error somewhere. There has to be a sign error somewhere. Okay, maybe it's okay. It's okay. Okay. So this identity is fine. So when you plot it out using the right hand side, you get something like this, or you can square cosine theta in your head. If you square that in your head, you get something like that. Okay. Cosine theta will look something like this. If you square that cosine theta, you get cosine square theta, which looks something like that. So you find that PT is actually a sinusoidal function riding on top of a DC value. What is that DC value? What would this sinusoidal function average to? Half of the peak values, right? You can see that visually. You can see that visually that if I were to take the average of this signal, it will average to that value over there. Okay? So, we like to introduce the concept of average power instead of giving you the instantaneous power, because instantaneous power is not a constant for a sinusoidal signal. So it's much better to give you this value. What you receive in your home is actually an AC signal, AC voltage and current that passes through your house, and it actually produces power that looks like that, which is not a constant. But you have been charged for this value. Okay, when you pay the utility companies, you pay for the power that is delivered to you, which is the average power. So let's talk about average power then. In order to talk about average power, let's define what it is. It is the time average power would be the time average of an instantaneous power, which is given by Vt, It, dt from t equal to 0 to t, where capital T is the period. It's the period of this power. Let's say if this period is this, okay, and let's call this our period. That is when the signal repeats itself. And if you average that power over that period, that is called the average power or time average power. And in order to compute this, you will have to say, in this very simple example, I introduce something with no phase lag between them. This is true for a current and a voltage across a resistor. But if you have an inductor or some other kinds of impedances, there will be a phase difference between them. Okay, there will be a phase difference between them. You may get something that looks like this. Instead of V naught cosine of omega t, let's make things simpler. And then the IT might be I naught cosine of omega t plus theta. Okay, there will be a phase lag between the two currents. I mean the two signals, V and I can denote that phase lag by just theta, and then I average this. And how would you integrate something that looks like that? It looks horrible, right? But if you know your trigonometric identity well, what would you do the first thing? You expand the second cosine using cos A plus B. And if you expand this second cosine, you get cos of omega t cos of theta minus sine of omega t sine of theta. Right? And then you substitute that back in, you get two terms. 1 over 2, 0 to t. I can put the V naught, I naught outside. Okay, I can put the V naught, I naught outside. And then what I have left inside is cosine of theta, cosine square of omega t for the first term, minus cosine of, or sine of theta, cosine of omega t, sine of omega t. And then integrate. But what would the first term integrate to? What would the first term integrate to? Cosine square omega t. If you could time average this first term, what did it time average to from this picture over here? Averages to? This is cosine square, right? Pictorially, you can see the answer already. If I were to time average this one, integrate over one period, and divide it by the time, this quantity will time average to half. Very good, Sebastian, very good. Okay? So, then, you can see pictorially I can do the math. Okay, you can do the math and then do the integration. It's much harder to do the math. It's much easier to see pictorially. Okay, so this will time average to half. But what about this term over here? How would I integrate that term? That term is difficult to integrate, but you invoke your trigonometric identity again. What is sine theta cosine theta? Is equal to? What is that? I know that sine of theta, sine of A plus A, using the trigonometric identities, sine A cos A plus sine A cos A, right? If I apply this trigonometric identity, so it means that this one must be half of sine 2 theta, right? If I apply that trigonometric identity. Okay? So this must be true. Hence I can combine this into half of sine of 2 omega t, which means that the frequency of this term has doubled. The frequency of this term has doubled. Actually, the frequency of this term has also doubled if you use this identity. That's why you see this. So if you were to plot the second term over there, it will be something that has both positive sign and negative sign as you plot it. This term, this function, goes for both positive values and negative values. So when you time average the second quantity, what do you get? You get 0. The first quantity, as you can see from this picture over here, does not go to the negative value. So it time averages to half. So this time averages to 0, and then this goes to half, and then you will have something like, pardon me if I write below the line. Okay? So it's half times t divided by t, so this is just half. And then there's a cosine theta involved. The second term just goes to be 0. Okay? And this is valid for any phase that you want to put between these two terms. Theta can be any value. Okay? And this is in general true. And hence what you have then is that you have this rather useful formula on finding the time average power. Okay? The time average power, if I were to write the first term in phasor form, it would be real of V naught e to the j omega t, and then it will be real of I naught e to the j omega t plus j theta. Agree? If I were to write this signal in phasor form, I will get these two to be true. And then the phasor quantity I have here is actually real of I e to the j omega t. And if I write this with the notation V e to the j omega t, then you can see that the time average power, okay, can be taken as the real part of V times I complex conjugated. Okay, complex conjugated. Okay. And so, divided by 2. Let's see if this formula holds true. What is V? V is just V naught. In this example that I have quoted, I is I naught e to the j theta. Okay, can you see that I is equal to I naught times e to the j theta? Can everybody see that? Okay? So if I were to substitute this formula in there, I will get real part of V naught I naught e to the minus j theta divided by 2. Okay? And if I take the real part of this quantity, I will get V naught I naught. This might be confusing to you. Let me just erase it. Cosine of theta. If I take the real part of this quantity, it would be just cosine theta, right? If you apply the Euler's formula, you apply the Euler's formula with the fact that e to the minus j theta is cosine of theta minus j sine of theta. Okay, that is Euler's formula. So this average power formula holds true in general. Okay, holds true for any phasor quantities. Yes?
Why is V equal to V naught, and where did the complex conjugate for I come from?
Okay. I just want to quote and show you that this formula holds true by finding the time average power. I want to prove this formula to be a general formula next. Okay, let me do that proof next. Okay, so I did the time average power study over there, and I showed that that formula holds true. Okay, let's prove that formula, and let's prove that this is a general truth. This is a universal truth. Okay, let's prove that. So, instantaneous power is equal to VTIT. And if I write this in phasor form, and this will be general true for any phasors. Okay, V need not be just V naught, but V can be anything. Okay, times the real of I e to the j omega t. Okay, this is just another way. But how do I write the real part of a complex number in other forms? The real part of a complex number in another form is that itself plus its complex conjugate divided by 2. Okay, so I can write this as B e to the j omega t plus its complex conjugate, which is this thing over here. divided by 2. I do likewise for the second term. I will have I e to the j omega t plus I complex conjugate e to the minus j omega t divided by 2. Okay? Now I multiply these four terms, these two terms out, I get 4 terms. Agree? Let's figure out what the 4 terms are. Okay? You will have, let's multiply those terms where the e to the j omega t would cancel each other. So if I multiply this first term with the last term, I will get v I complex conjugate divided by 4. The e to the j omega t would cancel. And then I multiply this one with that term over there. I get v conjugate I divided by 4. Okay? This would be what I get. This term times that term equals that. This term times that term equals that. And then I have the crossover terms. The crossover terms will be this term times that term, which is vi e to the 2j omega t over 4. And then the other one, which is v conjugate I conjugate e to the minus 2j omega t over 4. Okay? What is this actually? What is this actually? This is just the real part of ei conjugate. What is this actually? This is just the real part of this quantity. So I can replace this long equation with just a shorter equation. And if I try not to write below this boundary, I try not to go below this boundary. Okay, then it says that PT, instantaneous power, is just the real part of VI conjugate over 4 plus twice the real part. Okay, I get twice the real part of this. Okay, when I add this together, I get twice the real part of that. When I add the other part together, I also get twice the real part of vi e to the 2j omega t over 2. So the 4 is being replaced by 2. But now you take time average. The time average of the second quantity will go to 0 because it's a sinusoidal function. The time average of the first term does not go to 0. Okay? So if I do time average now, which is to integrate over t, the above quantity in general, you can see that the first term just becomes itself because it's a constant. The second term vanishes. So I have this formula to be a general truth. So this formula that I have written down is a universal truth. Okay, a general truth for average power. Okay? And usually, you sometimes see in some textbooks this notation for time average power, using a square bracket to denote time average power, and that is written that way. Okay? So you can test this to see if it's really true for resistive network. For resistive network, V is equal to Ri for resistor. Okay, this is true. And then you can see that P average is equal to half the real part of Ri. V is equal to Ri times I conjugate, which is half the real part. There should be a real part here. Okay. And then this should be the half the real part of I times I conjugate give you I magnitude squared. Okay. Okay, and this is entirely a real quantity, so you can remove the real part. So this is r I squared over 2. Okay, so previously in resistive network, we learned that the power is I squared R. Okay, that was for resistive network. But for phasor circuit, there's a factor of 2 coming about. Because this was the instantaneous power. This is the time average power. The difference between instantaneous power and time average power is a factor of half. And always remember the factor of half when you want to calculate time average power. Okay? So what is important to remember is that this can also be written like that formula over there that you have learned previously in terms of R times I root mean square squared. If you define I root mean square to be 1 over root 2 of I, if you define the root mean square to be 1 over square root of I, which is the peak-to-peak value, this I will give you the peak-to-peak value of the current. This one is the root mean square value in the plot that I have given you before. Then this formula looks like your old formula that you have learned in resistive networks. Okay? And by the same token, you can also calculate that the average power in terms of the voltage, by the same token, is V root mean square square over R. Okay? And if root mean square square is defined to be the magnitude and always a real number, you don't really need that square. You don't need the magnitude sign. Okay? So you can write this as root mean square square times R, I square R. And these are the formulas that you are familiar with in resistive networks, but you have to replace those numbers with root mean square values. Okay? So what you have often quoted to you in an AC circuit, like the circuit in your home, that voltage quoted to you is actually the root mean square voltage. Say if you have 120 volts in your home, that 120 volts is not peak-to-peak voltage. It's the root mean square voltage. Okay? Because if you have a signal defined by this, e to the j omega t, then if this is purely real, then you have v cosine of omega t. And if you plot this thing, it looks something like this. And this is v, this is minus v. So this v is peak-to-peak voltage, sort of. Okay? And as you see before, if you were to square this quantity, you get something else. And you don't really get the power, average power, to be proportional to the peak directly by having to divide by 2. But if you want to write something that looks like resistive network, you have to actually give the root mean square value. Okay, root mean square value is actually v over root 2. Okay? The peak to peak divided by root 2, and that gives you the root mean square value. Okay, let's do some examples.
So what's the significance of root mean square value? Like, why do they give us the root mean square value and not the power, time average power?
Oh, this just makes you easier to remember this formula, right? Then you don't have to put a factor of 2. Also, it has some other connotation. It means that root mean square actually means that you square this signal and take its average. So if you square this signal, okay, you have v squared, and it will look something like this. And if you take the average, you get v squared over 2. Okay, you square it and take its average. Okay, so you can see that the average of v squared is 1 over root 2 v squared. No, root 2 v squared. So if you take the square root of this, you get 1 over 2v. Okay, that is the meaning of root mean square. Okay, you square the average, the square value, and taking the square root of it.
So
That's
why
where
is
the
this a
meaning
more,
root mean square come from.
so why is this a more convenient
Then you don't have to put in the factor of half. If you like writing the factor of half, then you always work with peak-to-peak values. Okay? If you work with root mean square values, you just forget the factor of half. And these formulas will just look like the formulas that you have previously learned in resistive networks. And that is the meaning of root mean square. That is where it comes from. Okay? So let's do an example. And one of the things that you should notice is that if a circuit is purely inductive or capacitive, then if I take the real part of this quantity for a purely inductive or capacitive circuit, say if you have an inductor, V is equal to Zi. And then for an inductor, this is J omega Li. This is for an inductor. And if you plug that in there, you get half real part of J omega L I magnitude square. And this is I magnitude square. And this becomes I square. What is the value of this real part of this quantity? What happens if you take the real part of this quantity? I hear some correct answer. Can you yell it out loud? 0, right? 0. Why is that 0? Why is the time average power that goes through an inductor equal to 0? Remember what an inductor is. Inductor is just an energy storage device. Okay? If you try to pump current through it, the current goes out of phase. And then magnetic field gets built up. Energy is stored in this inductor. But if you remove the current, then current tends to sustain itself and tries to flow. Okay? And then it tries to release the energy that's stored inside. So there's no time average power dissipated in an inductor. That's why this term evaluates to 0. Similarly, for a capacitor, then you have Z equals to 1 over J omega C is minus J over omega C. And if you plug that in, you also get 0. Okay? P average for a capacitor is also equal to 0. Why is that so? Because a capacitor is also an energy storage device. As you apply a current, a voltage flow, you get a current flow. But after a while, the current stops the flow, and energy stored in this device, okay? And there will be electric field built up with energy storage, and then the energy releases itself back and forth in different cycles. So things time average to 0, because if you work this out, it will be half the real part of Z is 1 over J omega C I squared. Okay, and it has to be 0. Okay? So, there is an example 4.22 in the textbook, and then you have this circuit over here. You have cosine of 2t, cosine of 2t. And then you have 2 henries over here, 3 ohms over here. So first thing is to convert this into a phasor circuit with a V of 1 volt, okay, 1 volt V, and then with a impedance of J4 over here, because omega equal to 2, and then R is equal to 3. And then you can find the current. I don't need to teach you how to find the current through this circuit, right? By this time you should know how to find the current. You find the current I, you know the voltage, then you can find VI conjugate, take its real part, half its value, that will give you P average. Okay? And just a lot of algebra and arithmetics. I'm sure you can struggle through them and get your algebra and arithmetics correctly. Okay, and the textbook also shows that the power absorbed by this circuit is exactly equal to the power given out by this thing. Okay, because I'm running out of time. The clock is ticking away, so I better go to the next topic. The next topic is on available power and maximum power transfer. Okay? This also has a slight twist from what you have learned in resistive network. And if you have a phasor circuit that looks something like this, okay, that you have already found a Thevenin equivalence, and you know what Z Thevenin is. Z Thevenin is RT plus J XT, and then you have a load over here, and let's call it ZL is equal to RL plus JXL. Okay? So how do I adjust the load so that I have maximum power transfer from the source to the load?
Set it equal to the,
What?
set it equal
To what?
to the Thevenin.
Not the same. Okay, that is where it departs from what you have learned in resistive network. The resistive network, you set this to that, and it works there, but it doesn't work here. Okay, so this is one departure from what you have learned in resistive network. But just a nomenclature. This is called a reactance. Okay, this is called a reactance. And sometimes you see Y written as G plus JP. Okay, this is called a conductance, and this is called a susceptance. Okay, let me write down those names for you. This is the conductance, and this is the susceptance. And the imaginary part of that is usually called a reactance. And let's go about working on this circuit and see how we should maximize the power transfer. Okay, how we should maximize that. And we can write down the power at the load very easily. The power at this load is just half the real part of the voltage across the load times the current passing through the load times IL conjugate, okay? So what is VL? VL, we can use the voltage divider formula. VL is VT times this thing divided by the total, okay? So it is given by CL over ZL plus ZT. What is IL? IL is given by, I have just used the voltage divider formula there, okay? And then how do I find IL? What is IL? VT divided by the total impedance of the circuit. Okay? So you can plug that in now. You get PL is equal to half times the real part of VL, which is VT ZL over ZL plus ZT times the conjugation of this. That's very important. Okay? ZL plus zt, but with the whole thing complex conjugated. Okay? Now we can do some simplification. This bt conjugate times bt gives me what? This term times this term is bt magnitude square, right? What about this thing times this thing? It gives the denominator magnitude square. Okay, so I can simplify this and say that PL is equal to half the real part of Vt magnitude square ZL over ZL plus ZT magnitude square. Okay, but what is the real part of the numerator? The real part of the numerator is just going to be giving you RL. Okay, and the denominator is it complex or real? The denominator that you see here, purely real. So I don't have to worry about any other thing except taking the real part of this quantity. So this is half Vt squared RL over this thing. And let me write out this in gory detail so that you can see what the answer should be. RL plus JXL plus RT plus JXT magnitude squared. Okay, so this is the power delivered to the load. How would I make this thing the maximum? To make it the maximum, I like to make the denominator as small as possible. Okay? One way to make the denominator as small as possible, the magnitude as small as possible, is a complex number with the real part and the imaginary part. Okay? It's a complex number like that. And to make its magnitude small, one way is actually the imaginary part can be squeezed to 0. If you make the imaginary part goes to 0, then its magnitude will be smaller. Okay? If it has an imaginary part,